Stuff that's due already, I guess. Okay, so we are doing centroids. And I gave you one example of using the integral definition. But I said that really you're never going to have to use that. I'm never going to give you a test problem where you have to figure out like an integral. So there are three facts that combine to make that integral definition unnecessary. So the first one is what I sort of showed you last time. So for a given shape, you can do the integral one time. And it gives you an algebraic formula that you can use forever after. After. There are a lot of people in the world doing a lot of integrals, and so you could never think of a shape that someone hasn't done somewhere, and has a formula for. So that's the first fact. And we did the one for a right triangle, and we found out that the centroid is a third of the way that way and a third of the way this way. Second, there's a relationship between lines, or in 3D, planes of symmetry and the centroid. So I'll talk about that today, and then that just says that if you have highly symmetric bodies, you don't have to do a calculation in the first place. You don't even need an algebraic formula. Yeah.
Could you get away with only using lines and triangles to find the centroid of anything?
Lines and triangles.
If you got any shape, you can break it up into a triangle in the 3D space, find the centroid of that.
Oh, I got you. Well, yeah, what you're talking about is kind of like numerically how you would do it, I think. I mean, you're talking about sort of like a shape filling, like a space filling shape. Kind of the same way you break up functions in defining the integral, you break them up into long rectangles or whatever. Yes, you can do that. And that is the third thing that that's important here to remember is that some formulas will let us express the centroids of complicated shapes. As a finite sum of the centroids of simple shapes. Okay, so one, we already did that one. So now going on to the second one, what's the relationship between the centroids and the lines or planes of symmetry? Oh, actually, let's just, right here, let me give you all of these formulas that you're going to need in this class. So for one, let me just give you a list of centroid formulas. For common 2D shapes. So the first one is a right triangle. That's the one that we calculated. And I'm going to give you the formula for the centroid along X, the centroid along Y, and then give you the formula for the area. So for a right triangle, the centroid's there. I'm going to call this X bar and this Y bar. And like I just said above, the X centroid is the base over 3. The Y centroid is the height over 3. And the area is just the area of a triangle, base times height over 2. And we're using that this is B and this is H. The next one is a quarter circle. Imagine if that were a circle. And the centroid I'll call this X bar and this Y bar. X bar is 4r over 3 pi. Y bar is the same. And the area is just the area of a circle divided by 4. So pi r squared over 4. And this is r. Yep.
Can you use that for an ellipse as well?
For what?
An ellipse. Small modification you can make, or is it just?
It's not immediately apparent to me what that small modification is, so I don't know.
I kind of don't think so.
Yeah, I mean,
I just remember seeing that like the area of ellipse is like famously hard.
the area of an ellipse. Well, it shouldn't be that hard by integrating because we know a formula for the ellipse. So
Yeah, if you do it in terms of radians, that wouldn't be bad at all.
yeah, even in terms of just slim rectangles, it seems like it shouldn't be that hard to calculate, but let's not do it. And then the third one is a semiparabola. So I'm going to think of this this way. Okay. And the centroid is over here somewhere. I'm going to call this distance A. And this distance H. And then this is X bar. And the long length here is Y bar. Then X bar is 3A over 8. Y bar is 3H over 5. And the area is 2AH over 3. Okay, so this is given in terms of sort of funny things that, I mean, that's not how you normally define a parabola, but just notice that it's not very hard to go back and forth between these parameters and the parabola function if you're given a parabola just as a function of x, okay? Okay, so what did I say next? Centroids. Okay, so 2, we're going to do this, talk about lines and planes of symmetry. In 2D, the centroid always lies along any line of symmetry you can find. So for example, and what that means is if you can find two lines of symmetry, in 2D, lines intersect if they're not parallel. So if you can find two non-parallel lines of symmetry, wherever they intersect has to be the centroid. Okay, so like for example, if you have a rectangle, this is a line of symmetry, this is a line of symmetry, and so the centroid has to be at the intersection. And that's why I didn't give any calculations for a rectangle in my list of shapes. I mean, that's going to be the most important shape that we do are rectangles, but you can just tell those from inspection. Another one is a circle. So I didn't put the centroid of a circle in there, but that's because what lines of symmetry can you find? One there, one there, one there, and they all intersect at the same spot. And that's just the middle of the circle, and that's the centroid. Okay. So if you know two lines of symmetry, The intersection has to be the centroid. If you only know one line of symmetry, I mean, if it can mathematically reduce the calculations you have to do from calculating 2 dimensions to just 1 dimension. It's not always the most useful thing. Like, for example, look at this quarter circle. This is a line of symmetry, right? And so you know that the centroid has to lie along that line, but that's not a super useful thing. It's really easier to just apply that formula 2 different times, instead of changing your whole, like, whatever coordinate system. And but let's say you had a isosceles triangle. You know that the centroid has to be somewhere along here, but you still have to calculate the height along that. Okay, what about 3D? It gets a little harder to visualize in 3D. But in 3D, the centroid always lies on any plane of symmetry. If you can find 3 planes of symmetry, those meet at a point. So those 3 planes intersect at a single point. And that point is the centroid. Centroid. Okay, so let me try to just draw a picture of this. So let's say that this is your 3-dimensional shape. And you have one plane of symmetry like this. One plane of symmetry like this. Bless you. And one plane of symmetry like this. And those 3 planes intersect right at the center like that. Okay, what if you had like a paraboloid? So something that projected onto any plane was a parabola. Okay, well, you can find planes of symmetry this way and this way, you know, infinitely many like that. And so you know that the centroid has to lie along a center line like this. Okay, and then again, you just have to figure out the height. Let's say the dotted line. Okay, and then the last one, the big one, we haven't talked about any of this yet, but third, there's some formulas we can use so that if we can break up a shape into a bunch of simple shapes and find the centroids of those simple shapes using, you know, our formulas or symmetry or whatever, then we can build up the complicated shape based on those. So, for example, if we wanted to approximate the centroid of this shape here, we could build that up. As a bunch of rectangles, find the centroids of all those rectangles. Okay, and then obviously the smaller you made those rectangles, the more accurate the thing would be, but this is just a way to approximate complicated shapes. And sometimes you don't have to approximate. I mean, sometimes you just have a, you know, what if you just had a shape like this or something? I don't know what that is.
Toast?
It is like toast with holes in it. But this one you could do exactly because you can find the centroids of those semicircles. I mean, you could think of it as 2 quarter circles each, and then we'll see that we can remove these 2 circular shapes and find the exact centroid of that. So this one would be an approximation. This one we could come up with exactly. And in 2D, it works like this. The centroid of the complicated shape is 1 over the total area of the shape times the sum of the centroid of the ith simple shape times the area of the ith shape. So this vector is the centroid of the ith shape. And it's important that you notice that this is, it's just the finite version of the integral definition. Okay, remember the integral definition was 1 over the total area times, I mean, think of it as an infinite sum of infinitesimal pieces, but those infinitesimal pieces, we're multiplying the centroid of the infinitesimal piece by that infinitesimal area. Now we just have the finite version. Okay, so if your life depended on it and you had to come up with a guess at how this sum formula worked, this is what you would come up with, or you'd be dead. And one thing that I'm going to show you is that you can do this as subtractions too. Like, so if you want to remove shapes, you can think of it as just a negative area. Okay, so let me get that in here. So you can just think of a removed shape as a negative area. And in 3D, just like in 2D, we just end up with a finite version of the 3D integral definition. So in 3D, the centroid, all three components are 1 over the total volume times the sum of the centroid of the ith shape times the volume of the ith shape. We're going to do a lot more 2D problems than 3D problems. And when we do 3D problems, nothing will be more complicated than just building up rectangles to get a total shape. So that's why I didn't give you any centroids of, more complicated, more involved shapes in 3D. You can do everything just with rectangles. Okay. So let me do an example. So let's say that this has a height of 1 meter and a width of 1 meter and a thickness of 0.1 meters the whole way. And I'm going to put my coordinate system here. So your answer always is going to depend on where you put the origin of your coordinate system and the orientation of the coordinate system. The answer you get is going to be the coordinates of the centroid in whatever coordinate system you've chosen. And I'm going to do this 2 ways. So I'm first going to do it as a sum of 2, thin rectangles. And then second, I'm going to do it as a large square with a smaller square removed. And since these are, we're not approximating anything, these are exact shapes that we can do here, we need to get the exact same answer for those two. Okay. So first, let's break it up into I'll break it up into a rectangle like this that goes all the way to the top. You could break it up a couple different ways, you know, but I'll have this red rectangle go all the way to the top, and then this second rectangle is going to be a little smaller. I'm going to call this one shape 1 and this one shape 2 just for bookkeeping. Okay, so what do we have here for dimensions? For the red rectangle, we have a height of 1 and a width of 0.1. And notice for this green one, we have a width of 0.9. And a thickness of 0.1. Okay. And so what do we know? For rectangle 1, if our coordinate system is at the lower left corner of this thing, I guess first let's calculate the area. And then second, let's calculate the centroid. So what's the area of this rectangle? Rectangle 1, centroids, we're in statics.
1, 1.
Yeah, so the area is 1 times 0.1. And then what about the centroid? Okay, so what about the x-centroid? How far from the lower left corner do you have to go to get to the x-centroid?
0.05.
Yeah, 0.05, right, perfect. And then how far up do you have to go from the bottom to get to the centroid? Yeah. And then rectangle 2. The area of that is 0.9 times 0.1, so 0.09.
Is that notation x bar vector?
Yeah, that's, yeah, I mean, that's just, I don't know if people use that notation, but that's just the vector components of this centroid. So the centroid is coordinates, but it's also a vector if you think of it as a vector from the origin to, you know, the same way coordinates you can always think of as a vector from the origin to the point. Okay, so in the x direction, how far do you have to go to get to the centroid of 2? This is a little complicated. You have to remember before you even get to the right, to the left edge of that rectangle 2, you have to cross this distance of 0.1. The total length of rectangle 2 is 0.9. So the centroid is going to be 0.45 from either side, right? But before you even get to the left side, you have to go 0.1. So this is going to end up being 0.55. You see that? With this stuff, there's a lot of just like that kind of manipulating, like, you know, how far do I have to go before this shape starts? A lot of times these will be turned the opposite way, and so you'll have to use the formula, but the rectangle's, you know, wall side is on the other side, so you have to subtract instead of add. Okay, and then the height, well, if you go all the way to the top, that's 1. The centroid is 0.05 from the top, so this is going to be 0.95. Bless you. Okay, everyone with me on that stuff? And now it's just a matter of putting it into the sum formula. So x bar, y bar is equal to the total area. Add these up. Is 0.19. And so we have 1 over 0.19 times the sum of 0.1 times 0.05, 0.5 plus 0.09 times the vector 0.55, 0.95. This is 0.287, 0.713. All right, so anything interesting you notice about this? That centroid, and so if this is homogeneous, that's also the center of mass. This centroid is not on a material location for this shape. So there's no reason that the center of mass or the centroid needs to be on actual material. And it makes sense if you think about like the centroid of a ring. You know from symmetry it has to be at the center of the ring and there's no material there. Okay, so this centroid is somewhere like this. One thing that's interesting about the high jump is if you track the centroid location of a good high jumper, when they get close to the highest bar that they can get over, their center of mass never for one instant goes over the bar. They get their whole body over the bar, but their center of mass just travels right under it. I know it sounds impossible, but it's sort of like this. Like so you can, how high you can jump determines how high you can get your center of mass. But if you could like get your arm over and then your elbow, and then you're breakdancing. You know, little by little, they snake one part of their body over and the rest of their body is way down below the bar. And the result is it never goes that high. Which, I mean, really explains why when people say like some old timers are like, the high jumpers have that funny technique, the Fosbury flop, where they go over backwards. It's hard to believe that's the best way to do it. And so like people are like, oh yeah, it's just because people didn't teach the Western roll or the old techniques the right way or whatever. But it's not really about that, because the Fosbury flop just lets you get so much of your body, so much of your mass below the bar, that it's just the lower your center of mass can be and still get over the bar, that's the best high jump technique, and that's what this is.
Cool.
Okay, so now we're going to do this the other way with subtraction. We better get the same thing. So this time we're going to go, we're going to think of it as a big square. And that's our shape 1. And then we're going to remove an inner square. And that's our shape 2. So we're going to remove 2 from 1. And so we're going to think of this square 2 as like a negative area. Okay. Okay, well, for square 1, we're going to calculate the area and the centroid. again, our coordinate system origin is going to be right at the lower left. So the area of that outer square is just 1. And the centroid is 0.5, 0.5. And then our square 2, the area of that, so this has side lengths of 0.9. So you can think of this area as negative 0.81. And the centroid, so we're going to go, the square has side lengths of 0.9. And so from either side to the centroid is going to be a distance of 0.45. For the x-centroid, before we get to the left side, we've already traveled 0.1. So this is going to be 0.55 for x. And then for y going up, it's just going to be 0.45. And now to get the total area, this is going to be 1 minus 0.81 or 0.19, you know, same area as we had before. So the centroid is 1 over 0.19. Times the area 1 times the centroid of that square, 0.5, 0.5. And then minus the area 0.81 times the centroid 0.55, 0.45. Any questions about putting that together? 0.287, 0.713. Any questions about that? Okay, so I said we're going to use centroids of center of mass. Well, we're going to use centroids for 2 calculations. One is to calculate the center of mass location of funny shapes, and then the second one is for distributed loads. So the first one, let me just start an example here. So let's say we have a shape like this. And there's a roller supporting it there. Let's say this is 1 meter. This is 1 meter. And this is 0.5 meter. And let's say the mass of this whole thing is 10 kilograms. What are the reaction loads? Those reaction loads are going to depend on where that weight force acts. So the first thing we have to do is calculate the centroid. Notice, by the way, that we could do this problem fine without calculating the y component of the centroid because the weight acts vertically. And so you can move anything along its line of action, you know? And so if its centroid is let's say the centroid is over here somewhere, we could apply that weight force anywhere along that line and it wouldn't change the problem. Okay, so that's sort of, that kind of thing can be a time saver sometimes. But let's just calculate both of them. Okay, so I'm going to break this shape up into a right triangle and a square. And when you're choosing your coordinate system, it's easiest for your centroid. It's a lot easier if you choose the one you're going to use for the whole problem. It doesn't matter where. I guess actually it'll probably make it a little simpler to put the coordinate system right here. So I guess that's what I'm going to do. It's not a big deal wherever you choose it, but you're probably going to want to stick with it for the whole problem wherever you put it. This distance is 0.5. This height is 1, 1, 1. I'll call this square shape 1 and this right triangle shape 2. So for shape 1, the area is 1. The centroid location is 0.5, 0.5. For shape 2, we're going to use the right triangle formula. And so, like, think of the directions you're going as in terms of, like, are you going from a point toward a wall or from a wall toward a point, you know? For the X centroid location, we're going like on this side. I think that's sort of like a right triangle that's like upside down from how we've drawn it before. But we're going to go 2/3 of the way from the point towards the wall vertically. Okay, and we're going to go 1/3 of the way from the wall toward the point in the X direction. That area is 1 times 0.5 divided by 2, so 0.25. The centroid is, the X centroid is negative, because we're on the negative side of the origin in the X direction. 0.5 over 3 is 0.16 repeating. And then 2/3 of 1, so this is going to be 0.6 repeating. Any questions on that? And then the total area is just the sum of these, so 1.25. And now I'll write this formula out. We'll finish this problem on Wednesday, but so the centroid is just going to be 1 over 1.25 times the quantity 1 times 0.5, 0.5 plus 0.25 times negative 0.16 repeating, 0.6 repeating. Your calculator, you can do all this right in your calculator. It'll do those vector calculations.
How do you input those?
What do you have, an 84?
3.
83. So you're going to have to go into that matrix environment
Yeah.
and define those
Gotcha.
vectors. It's easier on a 89 or an Inspire. Like on an Inspire, I just go to the vector thing and punch in the components, and you can put it all as a single, one line calculation with the plus signs in there, the parentheses in there. Okay, that's all.